So welcome back for part 2 of Sloss sequences. You're going to learn about who this guy is, Lawrence Sloss, and what the Sloss sequences represent and why they are so critical to historical geology study. You didn't learn about these in physical for a reason, because they are historical accounts of unconformities and rock layers that we have that tell a story about rise and fall of sea level. So let's get to it. So that brings us to Mr. Lawrence Sloss. In 1963, he published work about 6 major transgressive regressive cycles known as cratonic sequences. And a cratonic sequence represents a transgressive regressive cycle separated by a major unconformity. These allow geologists to tell the story of what happened geologically based on the stratigraphic rock record. In other words, the strata that was laid down while these oceans were coming onto the continent and while they were coming off. This diagram is from his literature, and we'll explain what it means here shortly. How do you read this diagram? First of all, you need to understand that this side of the diagram is the Cordilleran, or the western margin of the continental craton, North America. This side's going to be the Appalachian Mobile Belt. Every diagram's done a little differently. You can find a bunch on the internet, and they all say the same basic thing, but they may use a different color schematic. I like this one because it's easy to see. The black areas represent hiatuses or unconformable areas. In other words, we're missing sediment for these areas that are in black. A huge black like this means we got a huge unconformity. That means an area was not covered very long by an ocean, and it may not have even covered the middle at all. The brown and the white are essentially the same. The reason they alternate brown, white, brown, white, brown, white is so you can visually distinguish where the major unconformable contact is. These are areas, whether it's brown or white, that have sediments that were laid down during that transgressive regressive cycle. It's where we don't have missing rock record or unconformities. So the thicker the colored or white section, the more sediments were laid down. So you can see we got a pretty thick one. The thickest is actually Tippecanoe and Aruka and Zuni by far. The puniest of them is obviously the Tejas. So we'll be looking at all 6 of these all semester, but we're going to start today. So remember that the colors are just there for you to have visual acuity in terms of representing when the event of regression finished before the new transgressive cycle started. And each one should be separated by a major unconformable contact. So the first one actually starts in the late Precambrian. We'll get to why in the Precambrian lecture, but it has to do with the melting of snowball Earth. And then we're going to see a series of 6 of these for the rest of the semester as they appear in the rock record. Again, the black areas are the areas where we're missing some rock record, and notice they're more in the central part of the craton, and I mentioned why, because this area didn't get covered for as long, if at all, during that transgressive sequence. But the edges along the Cordilleran and the Appalachian Mobile Belt have less of the dark black areas because they were covered for a longer stretch of time, and thus they have thicker sequences of rock. When you read this map, make sure you're reading it right. I know I'm kind of harping on the same topic over and over, but this gives students issues, and has in prior classes, because they get confused. They don't understand why there's different colors for tan and white. Remember, the tan and white is simply a visual thing, just so you can see where the Sauk began, where it finished, where the Tippecanoe began, where it finished, where the Kaskaskia began and finished, where the Aruka began and finished, where the Zuni began and finished, and where the Tejas began and finished. The black areas are critically important for you recognizing that we had a major section of time where we're missing rock in the middle of the continent. So how do they work? Each sequence begins with a period of cratonic emergence, meaning there's no ocean coverage, just like you see in Yosemite right here. So they're characterized by erosion or non-deposition, which causes a major unconformity to form. And then you get a sea level that comes in, a transgression, and it starts to invade the continent with an Epeiric Sea and starts to deposit sediments. So let's say Yosemite gets covered with a Great Barrier Reef situation. I would start depositing ocean rocks on top of this. So at the greatest marine inundation, we get followed by a regression. Now, something I need to point out, as sea levels marching in during a transgression right at the shoreline, I should see these structures, and we still do today. These are stromatolites. And so stromatolite fossils are found all the way in during a transgression, and subsequently as the shoreline moves back out, we find them as well. So we can also find other clues like ripple marks and mud cracks and things that help us spell the story of where the shoreline actually was during the transgressive regressive cycle. But after the regression is complete and the Epeiric Sea comes off the continent, any freshly laid down material during that sequence is vulnerable to erosion, and that's how we create a major unconformity between one of the sequences to the next. The thickest unconformities are going to be on the areas of the edge of the continent, and you can see why here. This is a really good example of it. So you can see that this was all covered by ocean, and here this section's covered by ocean. So you're going to have thicker sequences here, but this area would produce that black part of the diagram because it's exposed and you're going to lose more of it. So unconformities near the edge of the craton span less geologic time because they are flooded. You don't usually see unconformities over here. You see them in the middle of the craton. Another thing to consider is what types of sediments are found where. Well, we'll visit this more as we go through the geologic time scale, but the sequences of types of sediments help us tell whether we were in a transgressive or a regressive cycle, and where the shoreline was or what type of rock was present in those time frames. So each one of these represents a grain size or a thickness of the type of material that was there. And keep in mind that the thicker the unconformity should be in the middle of the craton where it got covered the least amount of time with an ocean, if at all. So let's get to the 6 cratonic sequences. For test purposes, you obviously need to know when they began and when they end and what their names are. The Sauk is this one down here, starts in the late Precambrian with the melting of snowball earth. And this would have been the original craton right here, what we call the shield today. And this is the only places on the Cordilleran Belt and the Appalachian Belt that have sediments from the Sauk. So the Sauk has one of the largest unconformable contacts right there. During the Sauk, we get a perfect rock record of a transgressive sequence in the Grand Canyon because we get a Tapete sandstone, which represents the beach line, then we get a shale, which represents the lagoon, and then we get a limestone, which represents the far away from a terrigenous input, stacked one on top of the other. So we got this perfect look at a transgressive sequence. We'll look more at that during the Cambrian period. One of my personal favorite names is Tippecanoe. Tippecanoe starts in the middle Ordovician. So going back to Sauk, did you notice it went from Neo-Proterozoic to early Ordovician? That's test-related stuff. But for the Tippecanoe, it starts in the middle Ordovician, right in here, and goes all the way until the early Devonian. How do I know that? I can still see it's white. Do you see where we are right here with white? That's sediment that was laid down. Look at this thick coverage in the middle of the craton. Interpret that this way. If there's very little black for the Tippecanoe right here, that means it covered the entire craton. This was the biggest, most extensive, and probably deepest Epeiric Sea that we've ever seen in geologic past. It laid down water all over the place and filled all the basins, and the basins filled up with evaporites when the Tippecanoe regressed off. We'll be learning a lot more about that as we go through semester. So middle Ordovician for the Tippecanoe as its beginning point, and early Devonian as its final regression off the craton. Following the Tippecanoe, we had almost a repeat of Tippecanoe with Kaskaskia. It was a shorter duration of time, middle Devonian to middle Mississippian, and you can see there's even a period in the middle here where you get coverage of the middle of the continent with materials. So we actually have a place that has deposition in the middle, But you can see that it's thicker on the west side than it is the east. There's a reason for that. It has to do with mountain building. So sandstones during this time that were laid down as the beach marched into the middle of the continent were followed by extensive carbonate deposition in the middle of the Craton when we got a shallow epiric sea that looked like the Great Barrier Reef in the middle of the continental United States. Pretty amazing to think about, right? So moving on to the Aruka, we get from the late Mississippian all the way through the early Jurassic. This is a pretty long duration of time. It's broken into multiple segments. And you can see that white is deposited in the Aruka all the way up here to the very beginning of the Jurassic. But essentially, you can see a big white line in the middle, meaning we had pretty good coverage in the middle of the continent. But interesting enough, Aruka spells the story of Pangea. So during the Aruka, the theme is once we have the Mississippian complete, we start moving into a regressive sequence all the way through the early Jurassic, which represents the greatest eolian event of all geologic time. This cratonic sequence is dominated by lots of detrital sedimentary deposition, meaning sedimentary rocks that are things like shales, sandstones, siltstones, conglomerates that are along the continental margins where we had mountain building on both the Cordilleran and the Appalachian Mobile Belt. We had minor sea level rises and falls, especially in the eastern margin near the Appalachian Mobile Belt, which was responsible for laying down lots of coal deposits, which are found in cyclothems. So when we get to Pennsylvania, and we'll learn about cyclothems. So let's move into the Zuni. This is one of my favorites, really is my favorite, because I like the rocks. I like the name Tippecanoe, but Zuni produces this fantastic set of rock formations all throughout the Southwest. Technically, this stuff starts during the middle Jurassic and continues all the way to the early Paleocene. Probably gets, if you wanted to be more accurate, most of the deposition starts by the late Jurassic into the early Cretaceous. And by mid-Cretaceous, we had pretty good coverage. Zuni is my personal favorite because of the rocks that it makes in the Southwest. And these rocks are extensively beautiful. There's lots of carbonate deposition and even sandstone deposition. And you'll learn why, because there was a big oceanway that went right through the western section of the United States and made a big ocean there. And on either side was exposed land where you'd expect to see dinosaurs. And that's exactly what we find in the rock record. So you can see there's a big kind of black blob in the middle. Well, that makes sense. And then there's deposition through part of the middle, which was the western interior Cretaceous Seaway that we'll learn about when we get to that point in the semester. So this cratonic sequence started in the middle Jurassic and ended in the early Paleocene, which is Cenozoic. And it was likely caused by a mid-Cretaceous superplume that created a giant mid-oceanic ridge that displaced the ocean water onto continents. When it did, it caused a worldwide global rise in sea level, causing in some places up to 800 feet of water standing on the continent. It also was responsible for creating a massive seaway that separated the western and eastern sides of North America. The youngest and shortest and wimpiest of all of the cratonic sequences is the Tejas. But I say wimpiest, let me rephrase that and say shortest in terms of time. It provided us some extensive important resources economically, so we can't discount its credit. In other parts of the world, it laid down thicker sequences than it did in North America. This produced the smallest epiric sea on the North American craton. You can see that by how big the black is and how far it extends on either side of the Cordilleran and Appalachian Mobile Belt. Not the same story in Africa and Eurasia. A little bit more extensive rock deposition there. The Atlantic coastline only advanced up the Mississippi embayment. That's as far north as the sea transgressed. So most of the craton was exposed. That's why you see such a big black blob. Notice though you see white in the small section right in here, indicating that that's where that Mississippi River Valley would have been. So we will be learning more about each of these cratonic sequences throughout the semester, but you need to know when they begin and when they end for test purposes. So see if you can apply what you know. This is Lover's Leap area in Waco. Here's the limestone interbedded with shale in between. You can't see it because it's weathered away. Limestone and then shale, limestone. This gap is shale, limestone. So that's alternating layers of up and down sea level. It's recorded in a vertical rock layer. So you could be somewhere where sandstone and siltstones are exposed. Would you recognize the sandstone for the beach line? Would you represent the siltstone for the nearshore environment? If you had siltstone and shale showing, would you represent the siltstone as nearshore and the shale as lagoonal? The point is the rock record tells the story, and you need to be familiar with how that's interpreted. So looking at this right here, this is Hawaii's coastline. So let's say we get a rise in sea level and we bury this area right here, this coastal community. And let's say the sea level comes to here. So now I have what used to be exposed land covered by water, which would be a transgression. If I lower sea level, let's say I lower it to here where my arrow is, part of the coastline that's exposed would now, or that's covered now, would be exposed. All and up and down these coastlines are pillow basalts from where lava spilled into the ocean during volcanic eruptions from Kilauea. So you would expect to see exposed pillow basalts. My point is this. When we use all the clues together that the rock record has to offer, we have a much better comprehensive story to tell. See you at the next lecture. Make sure you know the start and finish dates of all the Sloss sequences and understand how to read that Sloss diagram. Bye.